My topic for the seminar is Flexpad, and my name is Priyanshi Srivastava. I am a third year BTech student currently pursuing my undergraduate degree in the field of computer science. I am an avid learner who is actively trying to acquire skills and looking for opportunities to further enhance my existing skills and develop more interest in this field. Bennett University is a popular, serene, 68-acre modern campus which was established in 2016 and is affiliated with UGC. It is a philanthropic initiative of the Times of India Group, the leading publishing house of India. 30-plus programs and 50-plus technology leading specializations in engineering, management, media, law, and liberal arts have made Bennett University the most sought-after recruitment destination among leading corporates in a short time, leading to a stellar placement record. The university fosters a proactive environment of innovation and entrepreneurship while enhancing skills in all areas of education through the internationally acclaimed centers of excellence such as Center for Innovation and Entrepreneurship (CIE) and Center of Executive Education (CEE). In addition to the development of students across all the areas, the university has a great track record of placing its students with top industry giants such as Adobe, Amazon, Amio, Applyboard, Cadence, Capgemini, Dell, Pico, and Hitachi Consulting, among others. Now, diving into the topic, let's talk about Flexpad. What is a Flexpad? Well, as the name suggests, Flexpad are highly flexible bending interactions for projected handheld displays. It is an interactive system that combines a depth camera and projector to transform sheets of plain paper or foam into flexible, highly deformable, and spatially aware handheld displays. We present a normal approach for tracking deformed surfaces from depth images in real time. Flexpad overview, or about Flexpad. It captures deformations in high detail, is very robust to occlusions created by the user's hands and fingers, and does not require any kind of marker. As a result, the display is considerably more deformable than in previous work on flexible handheld displays, enabling novel applications that leverage the high expressiveness of detailed deformation. We illustrate these unique capabilities through three application examples: curved crosscuts in volumetric images, deforming virtual paper cut characters, and slicing through time in videos. Resulting from two user studies show that the system is capable of detecting complex deformations and that users are able to perform them quickly and precisely. Now, Flexpad overview. Flexpad enables users to interact with highly flexible projected displays in interactive real-time applications. The setup consists of a Kinect camera and a projector and a sheet of paper, foam, or acrylic that is used as projection surface. Our current setup that is illustrated in the video has a Kinect camera and a full HD projector. ViewSonic Pro 8200 are mounted to the ceiling above the user next to each other and are calibrated to define one coordinated space. The setup creates an interaction volume of approximately 100 into 10 into 55 into 43 centimeters, within which users can freely move, rotate, and deform the projection surface. The average resolution of the projection is 54 dpi. The user can either be seated at a table or standing. The table surface is located at the distance of 160 cm from the camera and the projector. Our implementation uses a standard desktop PC with an Intel i7 processor, 8 GB RAM, and AMD Radeon HD 6800 graphics engine. While we currently use a fixed setup, the Kinect camera could be shoulder-worn with a mobile projector attached to it, as presented in Alloying or mobile or nomadic use. The key contribution of Flexpad is in its approach for markerless capture of a high-resolution 3D model of a deformable surface, including its pose and definition or deformation. The system is further capable of grabbing 2D image contents from any window in Microsoft Windows and projecting it correctly warped onto the deformable display. Alternatively, it can use 3D volume data as input for the projection. The detailed model of deformation enables novel applications that make use of varied deformations of the display. Sheets of many different sizes and materials can be used as passive displays, including standard office paper. In our experiments, we used layer-sized sheets of two materials that have demonstrated good haptic characteristics. The fully flexible display is 2 mm thick white foam. It allows the user to change between different deformations very easily. That is what concerns the flexible display material of the Flexpad. Now, coming to the implementation of Flexpad, existing image-based tracking algorithms on deformable surfaces rely on visible features. In this section, we present an approach that requires only image data from a kinetic depth sensor. This allows for tracking an entirely blank or arbitrarily textured deformable projection surface in high detail. Moreover, since the depth sensor operates in the infrared spectrum, it does not interfere with the visible projection no matter what content is projected. Our challenge of depth data is that it does not provide reliable image cues on local movement, which renders traditional tracking methods useless. The solution to this problem is a more global model-based approach. We introduce a parameterized deformable object model that is fit into the depth image data by a semi-global search algorithm, accounting for occlusion by the user's hands and fingers. In the following, we explain first, the removal of hands and fingers from the input data, second, the global deformation model, and thirdly, how a global optimization method is used to fit the deformation model to the input data in real time. Now, optical surface material analysis for hand and finger detection. While the user is interacting with the display, hands and fingers partially occlude the surface in the depth image. For a robust deformation, it is important to classify these image pixels as not belonging to the deformable surface, so the model is not fit into wrong depth value. The proposed tracking method is able to handle missing data, so the solution lies in removing those occluded parts from the input images in a pre-processing step. Due to the low resolution of the kinetic depth sensor, it is difficult to perform a shape-based classification of fingers and hands at larger distances. In particular, when the finger or the flat hand is touching the surface, the resolution is insufficient to differentiate it reliably from the underlying surface. Existing approaches used heuristics that work reliably as long as the back of the hand is kept at some distance above the surface. These restrictions do not hold in our more general case, where people use their hands and fingers right on the surface for deforming it. We introduced optical surface material analysis as a novel method of distinguishing between skin and the projection surface using the kinetic sensor. It is based on the observation that different materials have different reflectivity and translucency properties. Some materials, example skin, have translucency properties, leading to subsurface scattering of light. This property causes the point pattern, which is projected by the kinetic, to blur. This reduces the image gradients in the raw infrared image, which is given by the freenet driver. The display surface made out of paper, cardboard, foam, or any other material with highly diffuse reflection varies from skin in reflectivity as well as translucency. So low peak values or low gradient values provide a stable scheme to classify non-display areas. The projector inside the Kinect has a constant intensity and the infrared camera has a constant shutter time and aperture, hence the brightness. Now this shows the modeling of the deformable surface. Dimensions of the deformation model are given on the left as shown in the video, and examples of deformations that it expresses are shown on the right as shown in the video, respectively. Now, like everything, Flexpad also has its limitations of usage, like trap deformations directly observed from kinetic sensors. Secondly, trade-off between tracking stability and set of detectable deformations. Also, there are its applications, and now let's talk about the technology used. Applications, it comes with a very high flexibility, and the second advantage is 1:1 mapping. Now, the tech boundaries. The tech utilized is light space, Kinect Fusion, OmniTouch, and proxy studies. Exploring and analyzing volumetric datasets, as given in the figure. Animating virtual paper characters. To demonstrate the wide applicability of highly deformable handheld displays, we present an application for children that leverages deformation as a simple and intuitive means for animating paper characters in an interactive picture. By deforming the display and moving it in space, as shown in the figure, the creature becomes animated. High-resolution deformation allows very individualized and varied animation patterns. Once animated, the creature is released into the virtual world of the animated picture, as shown in the figure, which is the B bar. For example, fish may move with different speeds and move their fins. A sea star may lift some of its tentacles. A sea worm may creep on the ground. A flatfish may meander with sophisticated waveform movements, and seaweed may slowly bend in the water. Such rich deformation capabilities can easily be combined with concepts from previous research on animating paper cutouts that address the skeleton animation, eye movement, and scene lighting. Also, 3D models could get animated by incorporating as rigid as possible deformation. It is worth noting that our concept can be readily deployed with standard hardware, which is very good. Now, slicing through time in videos by deformations, as you can see in the figure. Now, the evaluation. There are two types of evaluations done. First is on the basis of tracking performance, and second is on the basis of user performance of deformation. First, tracking performance. Classification of skin. On top, depth input, center, infrared input, bottom, depth image after classification with skin parts removed. This is what tracking performance looks like. Now coming to the user performance of deformation, you can see in the figure. Next are the results, where average trial completion time is given in seconds and error bar shows the standard deviation. Conclusion. Summary of study findings. Highly flexible displays and dual deformations obtained with precision level of ±6 degrees or more. High accuracy. Average error was below 7 mm. These are the results or the findings of the previous performance tracking or user performance of deformation. Now, a logical extension of Flexpad is touch input. With respect to this question, future work should address several challenges. Technically, this involves developing solutions for Kinect sensors to detect touch input reliably on real-time deformable surfaces. On a conceptual level, and building on Dijkstra's algorithm, recent work, this also involves an understanding of where users hold the display and where they deform it. This is required to identify areas that are reachable for touch input and to inform techniques that differentiate between touches stemming from desired touch input and false positives that result from the user touching the display while deforming it. Any informal analysis from our study data showed that users made single deformations almost exclusively by touching the display close to the edges on its backside. This also helps for dual deformations with a fully flexible display material. This suggests that the touches in the center area of the display can reliably be interpreted as desired touch input. In contrast, the participants touched all over the display for dual deformations with a shape-retaining material. A simple spatial differentiation is not sufficient in this case. More advanced techniques need to be developed, for instance based on the shape of the touch point or on the normal chords involved. Well, based on the previous findings, touch input on deformable displays, desired touch area is better at the center. Active flexible displays, available displays are limited. Smart materials need for more deformable and stretchable. This was all what Flexpad was about. I'm sure I was able to explain its use and what is a Flexpad actually. Thank you.